Okay, so I'm just looking at this question. So it's an equilibrium question. First of all, it's asking us to find the equilibrium constant using concentration. All right, and we have zero point 0.1 mole of nitric, zero point 0.1 mole of hydrogen gas, zero point 0.1 mole of water, so that's nitrous oxide, sorry. So volume of 1 liter at 300 degrees Celsius. So if we're finding the equilibrium constant, we need to use the ICE method, and we'll go through that now. So first of all, I'd suggest we write out the chemical equation. I know it's up there, but it is, I find it easier to write it out again. Also, it's a good habit, just in case, it's not balanced properly or you need to balance it. Of course, we have the reversible reaction arrows. To H2O gas. Alright. Alright, now then we can write out the number of moles. Right, 100 mole, 0.051 mole. We're obviously getting that from here. Alright. Now, so this is the initial, sorry. So the ICE method asks you to find out what is initial, alright, and then the concentration ratio, and then at equilibrium, right? So the initial, as you start off, you have 0.1 mole of that, 0.051 moles of that, and 1 mole of water. Oh, sorry, 0.1 mole of your water. Now you actually have 0 moles of your nitrous gas, don't you? That's the beginning of the reaction. The reaction hasn't really occurred yet, so that's where we are there. Now this one's a little bit tricky because it gives you, first of all, the easy version of these questions is one product, one reactant. How much of that product turns into reactant. But this gives you 2 products and gives you both of them, and it gives you some of the product as well, right? So you end up with this product over here, and it feels like that should complicate the problem, but it actually doesn't. You need to follow the same ICE method. So what we need to recognize is that we're going to lose some X over here as the reaction occurs, because it's going to run in this direction because there's 0 moles here, right? We're going to lose some X here, and we're going to gain some X, and we're going to gain some X here. And we're going to gain the X in the same kind of ratio as the mole ratio. So we're going to gain 2X on these ones and 1X on these ones, right? We got that ratio just from here, okay? So, but we don't know what X is, right? We don't know how much of it they're actually going to gain, except for the fact that it gives us here the concentration of nitrous oxide was 0.062 at equilibrium. So in the equilibrium kind of row here, we know that the nitrous oxide ended up being 0.062 molar. Now, how much does that help us with finding out the actual moles? We need to turn that into moles. Well, it's moles per liter. We know that's a 1 liter container, so it ends up being 0.62 moles, right? Times that by 1 liter. Yeah, and remember that molar is the same as mole per liter. Yeah, times that by 1 liter, and then you end up with moles. All right, so how can we find X from all this? Well, yeah, we can, because we know that we started off with 0.1 mole, right? We know that we minus 2X, right? And then we ended up with 0.062. So let's write that out. We start with 0.062 mole. We minus 2x, and we ended up getting 0.062. Right? If we solve for x, right? So using our calculator here, we can minus both sides by 0.1, so it's 0.062 minus 0.1, yeah, and then divide by minus 2, yeah, we end up with x equaling 0.019. Okay, so then we can do the same for the others. We just kind of draw a table down here. Okay, sorry, I'll try to keep within the lines from now on. So this one was 0.051 minus 2x. Well, we don't know what that equals, so it's that times 2, isn't it? Yeah, so 0.38, so it's 0.051 minus 0.38, yeah, so 0.051 minus 0.38 0.038 probably, yep. Equals, at equilibrium, we end up getting 0.013 mole, right? Well, this is just 0 plus x, isn't it? Yeah, so 0 plus x, and x is 0.19, so this is 0.019 mole. Yeah, this is 0.1 plus 2x, well 2x is 0.038, yeah, so it's 0.100 plus 2 times 0.019, right? That ends up being 0.138, doesn't it? Mole, right? And now we wanted to bring it back to our concentration, right? Well, we were given this concentration, 0.062 molar, right? Moles per litre, it's 1 litre, so therefore it's the same number really, isn't it? Because we divided by 1.13 molar. 0.019 molar, 0.138 molar. Alright, so now we have the concentrations of each of these gases in the system. So now we can go ahead and calculate the equilibrium constant, right? So the equilibrium constant is calculated using those concentrations, right? And it's the concentrations of the products divided by the concentrations of the reactants. Because remember, it's yeah. So the concentration of N2 multiplied by the concentration of H2O. Right, now importantly, right, there's 2 here, so we need to square the concentration of water, right? So and the concentration of nitrous oxide squared times the concentration of H2 squared. All right. So let's plug those numbers in. So 0.019 times 0.138 squared. All right. Nitrous oxide is 0.062 squared times 0.013 squared. Okay, plug that into our calculator. Got a bit more room here. Can't easily see the calculator. No, okay. That's a bit better. So we have, might as well put it in brackets. 0.019, right? That's not squared. 0.138, that is squared, divided by 0.062 squared times 0.013 squared. And we can see here, we end up with 556.98. We might as well write a 2, 6, right? 8, yeah. So we need to figure out a few things from here. First of all, we need to figure out the number of significant figures. Well, really, a lot of what we're doing here is multiplying and dividing. So we need the lowest number of significant figures that we're given. The lowest number of significant figures we're given is 2. So we need to bring this down to 2. So we end up with equals 5.6 by 10 to the 1, 2. Yeah. Then we need to figure out units. So the way you figure out units is you substitute the this equation for the units of that equation. So it's molar times molar squared over molar squared times molar squared. If we simplify that, we get molar cubed over molar to the 4. Simplify that, we get molar to the negative 1. And that's what we use for our unit. We have 2 significant figures because we had 2 significant figures there up in litres. We have molar to the negative 1 because that's the units that I'm figuring out. And the important thing is that obviously with different systems, we would have different units for the equilibrium constant. And that's it. If you have any questions, you can email me or talk to me on Teams.